All right, so hopefully you've been practicing free body diagrams. It's really important to get these concepts and look at these problems as more than just a math problem. Because it's not just a math problem. We are totally mathematically modeling physical situations. But our basic equation is that the net force on an object is equal to its mass times acceleration. That's where we can start all problems. So we need to understand and be able to reason through the forces that are acting on any given object and how they are working together to result in the acceleration of the object. So I want to go through some conceptual questions relating forces and the subsequent motion. This is going to be similar to the free body diagram practice questions, but they're going to involve more than just recognizing the free body diagram. So we will be still looking at the free body diagram, what forces are acting on the object, but relating that to what the object is doing. So let's start with this question. So we have an object. Hopefully you've gone through and chosen what you think the answer should be. We're told that the net force on this object points to the left. So overall, if I was to draw a vector representing the net force, it would point to the left somehow. I don't know how long, I don't know how far to the left, but it has to point to the left. They've given us in this picture 2 of the 3 forces. We need to choose which of the options below would be the missing third force. So by saying our net force will point to the left, that means there is no net force in the y direction. So we need a downward force that has the same length as F1 so that those balance each other out or cancel each other out, whichever way we want to word that. We want that upward y component of F1 to balance out the y component of F3. All right, second part. Forces are vectors, so we have to think of them in terms of components. Just like position, we had to think xy components. Velocity, xy components. Forces are vectors, so we have to think xy components. In the x direction, we need the forces in the x direction to add up, giving us a result that points towards the left. So I know I need a x component pointing to the left, but if I draw it the same length as F2, they would balance each other out. This component pointing to the left needs to be at least a little bit longer than F2. It could be much longer. It could be a lot longer, barely longer. We don't have enough information to know. But we know that a vector that has an x and a y component, if I draw them head to tail, this vector would have to point down and to the left. So option A is not valid, option B is not valid. We need to choose between C and D. Hopefully, we can see that C, option C, needs to be correct. The reason for that, if I were to draw out option D, this x component would be really short. It would be shorter than F2, which would give us a resulting net force in the x direction pointing to the right. So that is why C is the correct answer here. Let's look at another question. Please pause the video, determine what you think the answer is. That's part of the learning process, is being able to look at what we think we know or do know and compare that and see if we are thinking correctly. We learn better if we have to confront our wrong answers. All right, so our cart, again, this specific problem doesn't ask us to draw a free body diagram, but I'm going to, just for the practice sake. Our cart is the object of interest. We're told that it is pulled to the right with some sort of constant, steady force. This force is constant. It could be 10, 20, 1.5, but it stays whatever number it is the whole time. The cart, of course, will also be feeling or experiencing the pull due to gravity. So downwards, our field force. The cart is on a surface, so there is a normal force perpendicular to that surface. There technically could be some friction that would oppose the motion. This would technically be what we call a rolling friction, because the wheels will be rolling on the surface. Rolling friction and kinetic friction are always constant values. As an object moves on another surface. Static friction we'll talk about later. It's not always constant. Anyway, we have this cart being pulled to the right, normal force up, mg down, maybe a little rolling friction, which is going to be very small compared to the pulling force. We know the cart is staying on this track. We know the net force up and down, the vertical up and net force is 0. So the normal force has to balance mg. This constant force to the right and a constant rolling friction will give us a net force on the cart that points to the right. Because this pulling force is constant and rolling friction and kinetic friction are always constant, given the object on a specific surface, this net force is constant. The question, though, is asking us about the acceleration. Notice our graphs are labeled a sub x, and that's because we know the only acceleration the cart's going to have is in the x direction. To relate acceleration to force, we have the net force equals ma. We can write that as a, the acceleration in the x direction, is equal to the net force in the x direction divided by the mass. This acceleration in the x direction is going to point to the right, simply because the net force points to the right. But in terms of what's happening to that acceleration, these graphs represent, the first one is that the acceleration is increasing. The second one, the acceleration is decreasing. The third one, the acceleration is the same value the whole time, meaning it's constant. So coming here, if this net force is constant, And the mass, this cart, it's the same cart the whole time. The mass will be constant. Then the acceleration has to stay constant. What that means is the velocity of the cart is going to keep getting bigger by the same amount to the right. It will speed up the same amount every single second. So relating forces to motion in terms of acceleration here.